How many of you like puzzles, like Sudoku and that kind of thing? Oh, you're going to love this next section then, because it's nothing more than a puzzle. And it can be a lot of fun if you're into puzzles. Or it cannot be a lot of fun if you hate puzzles. We're going to talk about circuits now. Circuits. So a simple circuit must contain a couple of things. So I'll draw a little simple circuit. So a very simple circuit. What's that? Battery. That is a wire. There's a resistor. That is a simple circuit. So it must contain a couple of things. Must contain one power supply. Some source of electrons. Without it, it's just a dead wire. A conductor, which is a fancy way of saying wires. Something that moves the electrons. We must have some sort of load. In this case, I have a resistor up there. That's a resistor. Doesn't have to be a resistor. It could be a light bulb, a motor, something, but it has to be something that uses up the electrons. Cause a voltage drop. Let me see. I'll put that. I like that. Something that causes a voltage drop. 4. And it's got to have a complete path. Because you can have 1, 2, and 3, but if they're not connected, that's not a circuit. It's an open circuit. It's not a circuit. By the way, when we have a circuit like this, and I know this is going to just kill everything. Yes, it did. If I had a circuit that looks like this, does it have a complete path?
No.
That is called an open circuit. That's an open. If it has something like that, it means it's open. It could be open on purpose. It could have a switch right there. There's a switch. But it's open. A lot of people say it doesn't work. Well, it's shorted. Well, a short is when you have a short cut. Like if I had a wire or something that went around like that, that is a short. A short. Short can be anywhere. It could be there. It could be up here. But it's something that finds a shortcut around the circuit. That is very bad. It causes wires to get very melty and hot and on fire. So shorts are bad. I'd rather have an open than a short. All right, so those are simple circuits. Now we're going to talk about Ohm's law. Ohm's law is named after Dr. Albert Law. That's a joke. It's named after Ohm. We're going to do Ohm's law and Kirchhoff's law. So Mr. Ohm, we've already talked a little bit about Mr. Ohm. Mr. Ohm said, well, there's certain units of electricity here. Well, he didn't say that, but we better review that. Units of electricity. What were my units? We've already talked about them. I have 1, 2, 3, and 4. We talked about 3 out of 4. Voltage. Which its symbol is?
E.
Echo. E. What else we got?
Currents.
Current, which is measured in?
Amps.
Amps. Its symbol is? I. We have ohms, which is resistance. Symbol is
Capital R.
R. Measured in ohms. So we got volts, symbol is E, measured in volts. Amps, symbol is I, measured in amps. Resistance, which symbol is R, measured in ohms. Represented by that, or that. There we go. Oh, number 4. What's number 4?
Watts.
What's number 4? See, that's another joke. He said watts. Not in the mood today, huh? Watts. With the W. Named after James Watt. All right. Ohm's law. Named after who?
Ohm.
Dr. Albert Law. Never gets old for me. George Simon Ohm. He died in 1854. And the law says the current in an electrical circuit is directly proportional to the EMF. What is EMF?
Electromotive force.
Electromotive force. Which one is that? Volts, amps, resistance, or watts?
Volts.
Okay, volts. It's proportional to the volts and inversely proportional to the resistance. The resistance is resistance. Well, what the hell does that mean?
V.
Well, it means the current in an electrical circuit is directly proportional to the EMF. Well, you can stop right there and say if voltage goes up, so does current. That's what that says. And the inverse is true. If voltage goes down, so does current. That's what that first part means. If the current in an electrical circuit is directly proportional to EMF and volts. And inversely proportional to the resistance, which is to say, if resistance goes up, voltage goes down. If R goes down, voltage goes up. Actually, to keep it, he says the current, so I should say, if I could say right here, current. That'd be better. I don't like voltage. There we go. Way better. Then we're going to talk about what is Ohm's law. Well, that is Ohm's law, but how about the formula? Well, there's the formula. So all I have to do is memorize that. Sort of. I can distill this thing down into 2 formulas for you to memorize, and as far as the rest of this program, all the way through your AMP test and probably most of your AMP career, all you have to do is know this, which is quite simple. It's not that simple. E-I-R. Remember that? E-I-R, in that order. E over I-R. And if we look at that and distill it down, all you have to do to know any one of these three things, if you want to know the volts, as long as you know two things, you can find the third. I'm going to say that about 100 times today. As long as you can find two things, the third is easy. If I have current and resistance, I can find volts. If I have volts and current, I can find resistance. If I have whatever, you get the idea. I forget where I left off. Follow? And what that is a formula that says E equals I times R. So if you want to know E, cover that up and go what's left, I times R. If I want to know I, guess what? I equals E divided by R. How about what if I want to know R? R equals E divided by I. How simple was that? You just learned 90% of the Ohm's law wheel. There's one more part of it because that did not cover P, which is also W, which is watts for power. And that is super simple. P equals I times E. That's pi. I like pi. So P equals I times E. If you can remember that I like pi, and if you can remember that right there, and you can, and you will, you are done. You've just memorized this wheel to the extent that you need for the rest of the program. And the AMP test. How great is that? There's not a single test question the FAA is going to ask you that these two things pretty much won't get you most of the way through. So, pretty cool, right? I can tell how excited you are. All right. So getting back to this, let me see. So Ohm's law goes on to say, or to greater define it, 1 volt causes 1 amp to flow through 1 ohm of resistance. Which is to say, E equals I times R, or I equals E divided by R, or R equals E divided by I. Now you will notice, if you watch me or pay attention, every time I have to do an electrical problem, and it's given to me, up at the top of my paper, I'll just put EIR. It's just so easy to put. I just put it up there, right there. I just wrote all my formulas. That way I don't get it wrong. R, E divided by I, can check that. I, E divided by R, E, I times R. There's nothing wrong with that. So I write it on every single page. To this day, I still write it on top of every paper because it's easy to do. And then I don't have to write pi because I can never forget the fact that I love pi. Well, so that is that. But when we talk about power, what is power? Power is defined as the watt. I use the formula P equals I times E. Obviously E times I worked, but then it wouldn't spell pi and that'd be very confusing. Let me think, do I want to do this? Maybe. That's the watt, yes. We will also deal to some extent, maybe not in this class, a horsepower. So the story, as I have it in my head, is this. James Watt invented the steam engine. And he had to sell the steam engine to the miners, not the children, but the people who got stuff out of the ground. So you have to equate this steam engine, you go to sell it, you'd say, well, I want you to buy my steam engine. Well, we're using horses. What's the equation to this, the horses? And so he came up with a formula whereby horsepower is 746 watts. How he came up with that, I don't know, but there he is. Actually, I don't know off the top of my head. So 746 watts equals 1 horsepower. So it was a way that he could sell his engines. How many watts would it be per horsepower? So, and all that being said, it was the amount of energy needed to raise 550 pounds a distance of 1 foot in 1 second. So we'll deal with horsepower at some point. You just have to remember it's 746 watts. Most of the time it's given to you. And if 1 horsepower equals 746 watts, then, and the question will be there. So as we get to know electricity a little bit, I would be remiss if I didn't talk about the dangers of electricity. Anybody ever been shocked? By the cops? Yes. No. All right. So we have across the street a magnetic particle inspection machine. I don't know, maybe you guys have seen it, maybe you haven't, but it's where we do non-destructive testing on steel parts. So if I put a steel part in there, such as a crankshaft, I'm going to put it between 2 copper braided lines, and I'll put it in there, and I will energize it, and I will put 1,000 amps per 1 inch cross section. So a 2-inch crankshaft is going to get 2,000 amps running through it. Now, as seemed to happen in my life all the time, as I'm sitting there working on the bench, doing magnetic particle inspection, it's done in a dark room under a black light. My eyes are adjusted. I can see what's going on, but inevitably the boss would always walk in to see what was happening. And I have there's a bar that runs the whole length of the machine that I would set up as part of the machine. Art has this too. You can just lean on the bar, so your hands are free. You can lean on the machine, and it energizes it. And there's a foot pedal that will release things. And so the foot pedal releases, and I would have a crankshaft where tens of thousands of dollars fall on a hardened steel bed. So I couldn't let that happen. So every time the boss would come in, I'm like, oh crap. I don't know why I just didn't yell, stop, don't come in. But he inevitably would step on the pedal and lean on the machine at the same time while I had to reach up and grab the crankshaft.
Oh.
So 2,000 amps. Never felt the thing. And I always wondered about that. And it wasn't until I bought this machine and I was talking to Magnaflux rep, and I said, I feel stupid asking it this late in my career, but how come I don't get shocked when I hang on to a crankshaft at 2,000 amps? And I said, it's real simple. Your skin is really calloused, believe it or not, most of us. Well, some of you have lived a charmed life, I can tell. So dry, callous skin actually has a lot of resistance. Our external body has a lot of resistance. So when you're grabbing this thing, you can't create electricity from nothing. So this is a whole nother class. But to get 2,000 amps, we use a transformer. It steps up the current, but it drops the voltage way down. Because a watt is actually I times E. So if you have coming out of the wall 100 watts, you can't create more than 100 watts. So 100 watts would be, just making up numbers here, so if we had 10 amps and 10 volts, that'd be 100, right? Okay, but if I double the current to 20, I'd have to have the volts to 5. And so one goes up, one goes down. So there's not a lot of voltage, can't get through your hands, so it's just all current, no volts. Although I've seen the machine arc across things, so anyway. So he said, yeah, that's why you don't die. And so let me see. So say that the external body has a lot of resistance. Remember yesterday I told you to grab the things at the 10,000 scale range and check your resistance? So there you go. So you did that. Did you write it down? It has a lot of resistance. So it takes more than a few volts to cause current to flow. Remember yesterday we talked about the makeup of the atom, and we had insulators and conductors. And we said, well, a conductor has less than 1/2 of its valence electrons, and a conductor has more than half of it. So our skin is more or less like a insulator. So it's going to resist current flow until the voltage gets to a certain point, then it flows. Just like anything. You get enough current through it, it works. Let's see. So our hand, your hand, a dry calloused hand, may have over 100,000 ohms because of that thick layer of dead cells on your hand. But your internal body has about 300 ohms. So I tell you that to tell you that if you're trying to shock somebody, you have to stick it in them. You got to stab them, get it inside there. I think that's why yeah.
So if you were to be shocked from the inside of your body, wouldn't you feel it like everywhere? Or just...
I think if you had two probes and somebody did it, you feel it across from here to here. The electricity doesn't flow. It's going to take the path. I don't want to say path of least resistance, but it's like that. I don't know. Want to try it?
Nope.
I wasn't saying you had to do it. You and I could pick somebody. You assign them. All right. Let's see. So given that, if you have 1 milliamp, which is 0.001 of an amp, because to unpack that milli, we go 3 places to the right, so that becomes 0.001 amp. You might have a little tingling. How many people lick 9-volt batteries? Explain some stuff. You get a little tingling. It's about 1 milliamp. I don't know what the resistance of a ton is. I've never tried it. 5 milliamps. 5 milliamps, but that's 0.005 of an amp. Let's see. That is the accepted max harmless current. It's not very much. 10 to 20 milliamps, which is 0.01 to 0.02 of an amp. Possibly you're going to get muscular contractions. Inability to let go. 10 to 20 milliamps. 100 to 300 milliamps. So that is 0.1 to 0.3 of an amp. That's all that is. May cause VFib. What's VFib?
Stop your heart.
Ventricular fibrillations. Your heart starts to flutter. And then I have 6 amps, but I hate my notes. Sustained VFib followed by an abnormal heart rhythm, temporary respiratory paralysis, and possibly burns. But you have to have the volts to go with it. If you don't have the volts, it's not going to matter. But once you combine the two, then you're in trouble. This is redundant. Let's see. 4. Let's see. See page 6. Wow, I wrote that several times. I'm like, this is a little redundant. 6. So I did it 3 times. All right, so we're going to talk about DC. We talked yesterday the difference between DC and AC, right? Okay. So now there are 3 types of circuits that we can talk about. Series, parallel, and series parallel. Series are the easiest ones. So we're going to talk about series first. Then we'll talk about parallel. And then in another class we do series parallel because they can be a little difficult. So we're going to talk about series circuits. A series circuit. Series circuit. Well, what's the requirement for that? Requirement. I think the requirement is, you guys want a break now? You kind of had one off the test. Yes? No? Okay. Everybody's afraid to say something, so I'll just make the command decision.
Sure.
We've only been talking for 26 minutes.